Hi everybody! In this video, we are going to be talking about phase diagrams. Now over here is a phase diagram, and a phase diagram simply tells you the main state of matter that exists at a certain external pressure and temperature. And what I mean by external pressure is the pressure that is, surrounding the solid, liquid, or gas depending on what you have. So for example, if I have a piece of rock and we are at sea level, then the external pressure is going to be 1 atm because that's the pressure at sea level. So the 6 phase changes that we have to learn or remember are fusion, which is solid to liquid, freezing, which is the opposite of fusion, vaporization, from a liquid to a gas, condensation, the opposite of vaporization, sublimation, the transition from a solid to a gas, and deposition, or the opposite of sublimation. So for the time being, ignore this dotted line on this phase diagram and focus on everything else. On the boundaries between each state, one state will be transitioning to another state. So, for example, the boundary between the liquid and the gas shows the boiling points at different pressures. So if you remember, the boiling point is when the temperature is high enough for a liquid to transition into a gas. So on this diagram, we have the solid area, the liquid area, and the gaseous area. And the transition from a liquid to a gas occurs on this blue boundary, which is over here. So let's take an example. The temperature where I think there's not supposed to be an A there, where the liquid turns into a gas at 1 atm is called the normal boiling point. So this is 1 atm, marked by that line over there, and at 1 atm, the point at where the liquid turns into gas, indicated by this arrow, will be known as the normal boiling point, and it's right here. And this would be the corresponding temperature to 1 atm on that blue boundary, and this temperature is known as the normal boiling point. And it's a special name because normal stands for 1 atm. So the normal boiling point is the boiling point when the external pressure is at 1 atm. So now let's try to figure out something else. What would be the normal melting point? Well, the normal melting point would be the temperature at which the solid turns into a liquid at 1 atm. So it would be over here on the green boundary, and if you go down, that temperature will be your normal melting point. Now, at these boundaries, the two states are at equilibrium, meaning that nothing happens overall, since the rate of the forward and backward reaction of the two states is the same. So, to clarify, let's take an example. When you're boiling, the rate of evaporation and condensation for a liquid at its boiling point is the same, and because of that, nothing happens overall at equilibrium on these boundaries. So on the red boundary, the blue boundary, and the green boundary, it doesn't really matter because in the end, you are at equilibrium on those boundaries. And the reason why nothing happens on those boundaries is because if you remember from last unit, when you increase the temperature enough, then the temperature will stop increasing, and that's when the phase change occurs. And during the phase change, all that happens is that the liquid will gain heat, for example. So in this example, we'll take a liquid, and during the boiling, the liquid will gain energy, and once it gains enough energy to become a gas, the newly formed gas will start to increase in temperature beyond the boiling point and break the equilibrium. So it will move to the right of the boundary. So in this example, this would be the boundary, and it will move to the right of the boundary, which is not at equilibrium anymore. So that's why it breaks the equilibrium. Now, the point of this example is to say that nothing happens on those boundaries where boiling, sublimation, or any of that stuff happens. So on this boundary over here, all that's happening is that the liquid is gaining energy. It's not changing, and therefore it is at equilibrium. But once it does change, then it breaks the equilibrium and it starts, changing temperature and moving to the right of the graph. So that's all for this slide. Let's move on to the next slide. The next slide will be talking about what exactly is going on, not on the boundaries, but within the regions. So again, this is the solid region, the liquid region, and the gaseous region. And now let's think about what states of matter exist in these regions. So in this gaseous region, which does not include this supercritical fluid region, it's like right here, and this entire region is only gases. So there are only gases in this region, and in these two regions, the liquid region and the solid region, you will have a solid and a liquid in each place, of course, but if we look at the liquid region will have a little bit of gas depending on the volatility of the liquid. And because evaporation occurs, and if you remember from the last video, evaporation is just the turning of solid or liquid particles on the surface of things into gases. And in these regions, although it's mainly dominated by a liquid, for example, there are also gases due to the phenomenon known as evaporation. And same goes for the solid phase. The solid phase does not only have solids, it might have a little bit of gas depending on how volatile the solid is. So the gas is due to, once again, the evaporation of the solid due to, the surface particles getting enough heat and turning into a gas and overcoming the vapor pressure. So evaporation is a cool phenomenon, and yeah. But the most important thing to remember is that in each of these regions, the dominating phase is going to be, the solid phase here, the liquid phase here, and the gaseous phase here. And the solid and liquid phase might be contaminated with a little gas due to evaporation. So now that we're done talking about the different states that might exist on this diagram, let's now talk about the different concepts. So we have something called the triple point. This is when all three states are in equilibrium, and if you guessed, it's when the three curves or boundaries intersect. So in this diagram here, the triple point is over there, and at this point, the solid, liquid, and gas are all at equilibrium, and essentially, you could become any of the three states at that point, depending on which direction you move. For example, if you decide to increase the pressure, maybe you decide to increase the temperature, or maybe you decide to decrease the temperature. All those decisions will determine whether you have a solid, liquid, or gas at the end. So, the critical temperature is the maximum temperature at which it is possible to have a liquid or a solid. So the critical temperature on this graph is over here, and it's the maximum temperature at which it is possible to have a liquid or a solid. So if we look at this graph here, if we go beyond the critical temperature, it will be impossible to have a solid or liquid. And in this graph, you could see that because if we go past here, it is impossible to have a liquid or a solid. We can either have a supercritical fluid or a gas, and we cannot have a solid or liquid beyond the critical temperature. Now, this is because above the critical temperature, molecules are moving too fast, and they overcome the intermolecular forces holding molecules together in the solid and liquid phase, and that's why they can never become those phases. So now we can talk about critical pressure. Critical pressure is the minimum pressure at which a substance can condense into a liquid at the critical temperature. So our critical temperature is here, and the minimum pressure at which a substance can turn into a liquid is going to be over here. So that's the minimum pressure, and the critical point will just be the intersection of the critical temperature and the critical pressure. Now we have to talk about this mysterious thing over here called the supercritical fluid. And these fluids occur when the pressure and temperature exceeds their critical values, which is why when you're beyond the critical temperature and pressure, you get this really cool region that looks like a box. And supercritical fluids have properties of both liquids and gases. So as a gas, it can effuse through pinholes in containers, and as liquid, it can dissolve stuff. So a supercritical fluid can do both of these things because it behaves as both a gas and a liquid in a way. And because of this, they are excellent solvents, which means that they can dissolve a lot of things while acting like a gas, which is pretty cool. Now let's clear up one misconception. The melting point and the freezing point mean the same thing because they both describe when a solid turns into a liquid or when a liquid turns into a solid. But regardless of what process it describes, it's part of, I guess, the same process, but they're just backwards, and they happen at the same temperature. So freezing and melting happen at the same temperature, and because of that, the melting point and the freezing point are the same. Now, this idea applies to the boiling point and the condensation point. Both of these ideas mean the same thing, and thus the boiling point is equal to the condensation point, since the temperature at which a liquid turns into a gas is the same as the temperature at which a gas turns into a liquid, because if you think about it, on a phase diagram, the transition between the two states happens at the same temperature. So for example, if the liquid was going to turn into gas over here, that temperature would be the boiling point. But what if it wanted to go backwards at the same pressure? Well, if it wanted to go backwards, then it would go that way. And notice that that point at which it intercepts is the point at which it boils or condenses, and that is the same as the boiling point. So the condensation point and the boiling point are the same exact thing. So let's move on to another topic. We will now look at the trends on the phase diagram. So, as we might know, increasing temperature will shift a substance from a solid to a liquid and then to a gas, and it might skip phases depending on what happens. So for example, at this pressure over here that I just labeled, you might notice that at this pressure, the solid will transition straight into a gas, and that is called sublimation. So sometimes it might skip phases. Now, increasing pressure is an interesting case. Pressure typically favors denser phases, so increasing pressure will cause the substance to want to conform to a more dense phase, since if you're more dense, you're more compact, and that's in response to the increasing pressure, because if you think about it, if you crumple up a piece of paper, for example, it will want to crumple up into a ball due to the pressure that you're exerting on it. So at low pressures, the substance is typically a gas because there's no external force to resist against gas molecules escaping into the air. So at low pressures, a gas typically forms, and it makes sense because of the reason I just said. Now, gases are also favored at low pressures because gases are not very dense. Now, as pressure increases, the gas may transition into a liquid or a solid, depending on which one is denser. If the solid is denser than the liquid for a certain substance, such as carbon dioxide, the gas will transition into a liquid and then into a solid, since the solid is the densest form. Now, the solid-liquid boundary has a positive slope. So in this example, you can see that the solid-liquid boundary has a positive slope. And in addition, you might also notice that for this arrow up here, as you keep the temperature constant and you increase the pressure, the phases go as follows: gas, liquid, then solid. So it goes in this order from least dense to most dense. Now what happens if the solid phase is less dense than the liquid phase? If this happens, then the gas transitions to a solid first, which is less dense, and then to a liquid, which is the densest form. So this solid-liquid boundary will have a negative slope. So let's take an example where the solid state is less dense than the liquid state, and water is a perfect example because the liquid state is more dense or denser than the solid state. And if we look at this graph, we can see that there is a negative slope on the boundary. And as you increase the pressure at a constant temperature, you can see that it transitions from a gas to solid and then to a liquid, and the liquid is the densest form. Now, to tell you the truth, this trend does not last forever. Now, this is the full phase diagram for water, and as you can see, it does have a negative slope at the beginning, but it stops working at extremely high pressures for things like water. So as you can see, at high enough pressures, the liquid-solid boundary reverts back to a positive slope, and it looks like density isn't everything once we get to high enough pressures. So yeah, let's move forward and look at a common misconception. A common misconception is that iodine sublimes at room temperature. Now, that might seem true by observing it, but in reality, iodine actually undergoes evaporation at room temperature, and that's weird for a solid to evaporate, but it does happen, just like water evaporates. And this happens because iodine has a very high vapor pressure. So it might seem that iodine sublimes, but in reality, it actually evaporates. So regardless, the process remains the same, either if it evaporates or sublimes, because in the end, all that's happening is that a solid is turning into a gas. Now, in reality, iodine actually melts and then vaporizes at 1 atm, so it does have a normal melting point and a normal boiling point, so it does not sublime at 1 atm. And let's move on to do a question now. So this is a phase diagram for uranium hexafluoride UF6, and it says which statements are correct. UF6 sublimes at atmospheric pressure, 2 at 80 degrees Celsius and 1.5 atm, only UF6 gas is present at equilibrium. So this is a chemistry Olympiad question, and it's designed to challenge us. So let's see if the first statement is true. UF6 sublimes at atmospheric pressure. Now, atmospheric pressure means at 1 atm, because that's the pressure that our atmosphere exerts. So at 1 atm, it looks like, well, this will be solid and liquid and gas, and it looks like it transitions from a solid straight to a gas at 1 atm, so it definitely does sublime. So 1 is true. Now, number 2. At 80 degrees Celsius and 1.5 atms, only UF6 gas is present at equilibrium. So if we take a look here, we see that at 1.5 atms and 80 degrees Celsius, it is in the gaseous phase, and at this phase, it definitely will not be at equilibrium between a liquid and a gas, since it is not on this boundary, and therefore it will only be a gas. And note that gases do not evaporate because gases are already gases. So therefore, during this point, once the system reaches its equilibrium, or its, I guess, point where everything is steady, then of course only a gas would be present here. So in this case, the answer for this question is C. And you might be confused on why it says equilibrium. And the reason why it says there is equilibrium at this point is because equilibrium is essentially when everything stops changing and it just stays constant. So in this case, all of the gas will stay as a gas, and thus equilibrium will be reached because nothing is changing. Now, the equilibrium on this boundary is talking about the equilibrium between the liquid and gas phase, where it's like in limbo between a liquid and a gas, but it's not changing. So, misconceptions cleared, and that's all for this video. Have a nice day.